Hello viewers, welcome to our channel. With this lecture we are going to start a new playlist on the topic field theory. As you know that field theory is a very important and fundamental concept in abstract algebra, and this topic is very useful for the students at undergraduate level and postgraduate level. But with this playlist we are going to design a systematical lecture series for the postgraduate students who are doing their post graduation in the field of mathematics. So let's start with the definition of field theory, and we will cover that in this lecture: definition of a field, subfield of a field, and ring homomorphism from a field to any ring. Okay students, so let's start this lecture. This lecture is very elementary and introductory one to field theory. So let's start with the definition of a field. So basically, what is a field? A set with two binary operations addition and multiplication is called a field if, let this denote this set by f, if number 1 f under addition is an abelian group. And you know the definition of abelian group. It means there must be associativity with respect to addition, and there must be identity with respect to addition, and there must be commutativity with respect to addition, and every element has inverse with respect to addition. So f must be an abelian group with respect to the binary operation addition. And number 2, f star. F star means the set of non-zero elements of F is an abelian group with respect to multiplication. And number 3, distributive laws holds in F. That is, the binary operation multiplication is distributive over the binary operation addition. And in form of elements you can say that b plus c must be equal to a dot b plus a dot c, and you can write also that a plus b dot c is equal to a dot c plus b dot c for all a, b and c belonging to f. So if f satisfies all these conditions, then we say that f is a field with respect to the binary operation addition and multiplication. Usually these two operations are denoted by addition and multiplication, but it is not necessary that these addition and multiplication are usual addition. These operations may be different from the usual addition and multiplication. Okay, so this is the abstract definition of a field. So next we will discuss some examples of a field. If you see that the set of a rational number with respect to addition and multiplication forms a field. Similarly, the set of real numbers with respect to addition and multiplication forms a field, and set of complex number with respect to addition and multiplication forms a field. These examples are discussed at graduation level in various university courses. Okay, so one more example of a field is Z by PZ. Z by PZ means the set of these elements 0 plus PZ, 1 plus PZ up to P minus 1 plus PZ. So these are the in fact congruence classes, and this forms a field with respect to addition modulo P, or you can write this as addition modulo P, and multiplication modulo P, and this operation is denoted as P. I will deliver a separate lecture on this topic, that Z by PZ is a field with respect to addition modulo P and multiplication modulo P. So these are the examples of field. If you see that these are infinite field and this field is a finite. So let's discuss the definition of finite and infinite field. Finite and infinite fields. So a field is finite or infinite according as the number of elements in it. Okay, so if you have a field, you can decide that it is a finite field or infinite field according to the number of elements present in the field. Okay, so students, if you notice that if F is a field, then F under addition is an abelian group. So you can guarantee the existence of 0 here. So 0 must belongs to F. And similarly, F non-zero elements forms an abelian group under multiplication. So 1 also belongs to F. Okay. So it means if you talk about a field, then a field must have at least 2 elements. So every field has at least 2 elements. Therefore, the field has at least order 2. Okay. So it means you can say that there is no field having one element. Okay. So this is an important information regarding the number of elements in a field. So a field must have at least 2 elements. So before going for the definition of subfields, let's restate the definition of a field in one line notation. So you can restate the definition of field as a commutative ring with unity such that every non-zero element is invertible. So this is very popular definition of a field in one line, a commutative ring with unity such that every non-zero element is invertible. So let's discuss the definition of a subfield. So for the definition of a subfield, you must consider a field first. So let F be a field. Then a non-empty subset L of F is called a subfield. Is called a subfield of F. So it means here this is the situation that L is a non-empty subset of F. So L is called a subfield of F if L itself is a field under induced operations of F. It means F is a field, so there must be two binary operation, addition and multiplication. Okay, so if L is a subset, non-empty subset of F, then L is called a subfield if L itself is a field under the induced operations of F. It means operations comes from the field, original field, and L is a subset and it satisfies all the properties of a field, and you can say that L under addition is an abelian group. Number 2, L star, non-zero element of L, forms a group. Under multiplication. And number 3, distributive laws holds in L. So L satisfies all the properties which are required for a field, and being a subset, so it is called a subfield of F. Okay. Next we will discuss necessary and sufficient condition for a non-empty subset to be a subfield. So necessary and sufficient condition for a non-empty subset of a field to be a subfield. It means what are the direct ways to show that a non-empty subset is a subfield of a field. Okay, so let L be a non-empty subset of a field F. F is a field. Then L is a subfield field of F if and only if number 1, A B belonging to F implies A minus B belongs to F. sorry, let me replace this by L. A B belonging to L implies A minus B belongs to L. And number 2, A belongs to L and we have a non-zero element from L, then this must be A B inverse belongs to L. So these are two conditions, necessary and sufficient condition for L to be a subfield. Okay, it means in many problems, many situations, if you want to prove a non-empty subset to be a subfield, just what you have to do, choose two elements from L, show that their difference belongs to L. Choose again two elements, one A from L and second non-zero element from L. Choose one element from L and a non-zero element from L and show that AB inverse again belongs to L. So these are the direct ways or necessary and sufficient condition to prove that L is a subfield. So this necessary and sufficient condition directly follows from these two conditions. Okay, because you know that if L is a subfield of F, then L under addition is a subgroup of F under addition. Okay, similarly, if L star forms a group under multiplication, it means L star under multiplication is a subgroup of F star under multiplication. And this is the subgroup and you know that what is the subgroup condition? If G is a group and H is a non-empty subset of G, then H is a subgroup of G if and only if X and Y belonging to H implies X, Y inverse belongs to H. So this is the subgroup criteria, and if we say that L is a subfield, it means L under addition is a subgroup. Okay, and therefore this condition directly implies this condition, and similarly using again this condition we can say that this condition holds. So it means the necessary and sufficient condition follows from the definition of corresponding subgroups under addition and under multiplication simultaneously. Okay, now we will discuss some more results on subfield. So students, notice that every field is a subfield of itself, because every field, if we consider the field as a subset of itself, then it forms a subfield of itself. Okay, so now we come to the definition of proper and improper subfield. If a field has a subfield other than itself, then that subfield is called a proper subfield. Otherwise, it is called an improper subfield. Okay, so it means if L is a subfield of F, L is contained in F as subfield, and at L is not equal to F, then L is called a proper subfield, subfield of F. So this is the concept of proper and improper subfield of a field. If a subfield is equal to the field, then it is called improper subfield. Otherwise, if a subfield is properly contained in the field, then it is called proper subfield. Okay. Now we will discuss that intersection of a family of subfield is again a subfield. So this is an important result. Intersection of arbitrary collection of subfields of a field is again a subfield. So let's see the solution of this exercise. So first consider the field. Let F be a field. Now let F lambda belongs to capital lambda be a collection of subfields of F. It means every member in this family is a subfield of F, and we have to show that their intersection is again a subfield. So let L is the intersection of all these subfield. Okay. Now what is our claim? Our claim is to show that L is a subfield of F. This intersection is again a subfield of the original field F. Okay. So first, to meet the subfield criteria, we have to show that L is a non-empty set. Since each F lambda belongs to capital lambda is a subfield, because every member in this family is a subfield. Therefore 0 and 1 belongs to F lambda for each lambda belongs to lambda, because we have already discussed that in a field there must be two members. One is additive identity and one is multiplicative identity. Okay, so it means 0 1 belongs to every member, and therefore 0 1 belongs to the intersection, because 0 1 are the common elements for every member. Okay, and this is L, so this implies L is non-empty. Okay, now we will use the subfield criteria. For that purpose we have to choose two elements. So let A and B belongs to L. Okay, since L is the intersection of all members of the family, this implies A and B, these two elements belongs to the every member of the family f lambda for each lambda belongs to capital lambda. And since each f lambda is a field, okay, so each individual member is a subfield. Each individual member is a subfield. Therefore, using subfield criteria, this implies A minus B belongs to f lambda for each lambda belongs to lambda, because each f lambda is a subfield. Therefore, each f lambda under addition is an abelian group. Okay, so therefore, if we choose two elements, then their difference belongs to f lambda. Okay, and since A minus B belongs to each f lambda, therefore A minus B goes to the intersection. F lambda, lambda belongs to lambda, which is your L. Okay, so what we have shown that if we choose two elements from L, then their difference goes to L. Now second criteria, again choose A belongs to L and a non-zero element from the L. Choose one element from L and second element is non-zero from L. Okay. Now these two elements belongs to L and L is nothing but the intersection of f lambda, lambda belongs to lambda. Therefore, A and B both belongs to each f lambda for each lambda belongs to lambda. Since again each f lambda is a field and B is non-zero, therefore A B inverse belongs to f lambda for each lambda belongs to lambda, because each f lambda star under multiplication is an abelian group. Abelian group. Okay, so therefore, since each f lambda is a field, therefore AB inverse belongs to each f lambda, and if AB inverse belongs to each f lambda, then it is a common element, it goes to the intersection, then lambda belongs to lambda, that is L. So using these two subfield criteria, we can immediately say that this implies L is a subfield of L is a subfield of F. So this is the result, that arbitrary intersection of subfields is again a subfield. Now we prove an important and very useful result about fields. So this is again an exercise that a field has no proper ideal. What does it mean? It means that if F is a field and I is an ideal of F, then either I is 0 ideal or I is equal to F. It means a field has only two ideals, namely 0 and itself. So see the solution of this exercise. Let F be a field and I be an ideal of F. So we claim that either I is 0 ideal or I is just equal to the full ring F. Okay, so we have to prove if I is an ideal, then either I is 0 or I is equal to F. So if we suppose I is not equal to 0, then we have to show that I is equal to f. Okay, so if we assume that I is not 0, then it is compulsory to show that I is equal to f. Since I is ideal, I is contained in f. Okay, so it means if we want to show that I is equal to f, then we have to show that f is contained in I. So since I is contained in f, therefore we have to show that f is contained in I. Okay, so choose. Now since I is non-zero, this implies I has non-zero element. Okay, this implies there exist at least 0 not equal to A belongs to I. But I is contained in F, therefore A is a non-zero element of F. And F is a field, and in a field every non-zero element is invertible. Therefore this implies A inverse belongs to F. Because A is a non-zero element of F, F is a field, therefore every non-zero element has inverse in a field, because F is a field. Now you can assume that A inverse belongs to F, A belongs to I, and I is ideal. This implies A inverse is the element of the ring, A is the element of I is ideal. Therefore left multiplication from the ring element or right multiplication from the ring element goes to I, because I is an ideal of F. Okay, so this implies 1 belongs to I. So this is very important stage of this problem. 1 belongs to I. This 1 belongs to I will help us to show that F is contained in I. So now choose any element x from F. X from F. Now 1 belongs to I and x belongs to F. I is an ideal. This shows that x into 1 belongs to I, because F is a ring, I is ideal. So multiplication by the ring element from left side or right side goes to I, and therefore x belongs to I, and which shows that F is contained in I. Okay, so F is contained in I and I is already contained in F. Therefore we have equality. F is equal to I. So what is the importance of this result? If I state here that if an ideal of a ring with unity contains unity, suppose unity is 1, contains 1, then that ideal equals to the whole ring. This result is very important because it shows that there is no proper ideal containing 1. It means any ideal which contains 1 cannot be proper. That must be equal to the full ring R. Okay, so you should remember this result. This result is very applicable and very useful for further results. No ideal containing 1 be a proper ideal that must be equal to the full ring R. Okay, so in this result we have shown that if F is a field, then F has only two ideals, either 0 and itself. Now we will use this result to show our next exercise. So next exercise is that a homomorphism of a field into any ring is either a zero homomorphism or a monomorphism. This result is also very important from the field theory point of view, and this result will be frequently used in further results. So let's try the solution. I will show you two solutions of this exercise, two different ways to solve this exercise. So first, let F be a field and R be a ring. And let sigma be a homomorphism of rings. So what is our claim? We have to show that either sigma is a zero map or sigma is a monomorphism. Monomorphism is 1-1 homomorphism. Okay, so if we assume that sigma is not 1-1, so we are going to show the first method. In this method, we assume that sigma is not 1-1. So if we assume that sigma is not 1-1, then we must show that sigma is zero map. Sigma is a zero map. That is, we have to show that sigma x is equal to 0 for all x belongs to f. It means sigma must be 0 on every element of f. Okay, so what we have assumed, sigma is not 1-1. So if sigma is not 1-1, it means two different elements may have same images. So this implies there exist a and b belonging to f such that a is not equal to b, but sigma of a is equal to sigma of b. Okay, so let us define a new element c as a minus b. Then clearly c is non-zero because a is not equal to b, so c is a non-zero element of f. So it means 0 not equal to c belongs to f, but f is a field, so every element has inverse. So this implies c inverse belongs to f. Okay, Now we will apply sigma to this element C, and we will show that sigma gives you value 0 on C. Sigma of C is 0. So apply sigma at C, sigma of A minus B, because sigma is a homomorphism, therefore it will separate sigma of A plus sigma of minus B. Okay, so this is sigma A minus sigma B, but sigma A is equal to sigma B, therefore this is equal to 0. So what we have seen? We have seen that sigma gives value 0 on this element C. Using this fact, we will show that sigma gives value 0 on every element. Sigma is 0 on every element. Okay, so let x belongs to f be any arbitrary element, then x can be written as C inverse x. Okay, there is no harm in writing this because C into C inverse is identity element. Now apply sigma at x, then this is equal to sigma of C inverse x. This is equal to sigma of C, separate this because sigma is a homomorphism of rings, so sigma will separate C inverse x. But we have seen that sigma of C is 0, sigma inverse Cx. So this is 0. So it means sigma is 0 on every arbitrary element x. Okay. So this implies sigma x is equal to 0 for every x belongs to f, and therefore sigma is a 0 map. So this completes the proof of this exercise. This is one proof. Now second proof is based on the concept of ideals. So let's see the second proof also. Now for second proof, let's write again. Sigma is a homomorphism from the field to ring R. Then we know that if sigma is a homomorphism, this is very usual concept, then kernel sigma is an ideal of the field F. But we have shown in earlier exercise that a field has only two ideals, either 0 or full F. Okay, so since a field has only two ideals, namely 0 and F. So kernel sigma is ideal, therefore kernel sigma has only two choices, either 0 or kernel sigma is equal to the full ring F. Okay, now if we thrash all these two cases, if kernel sigma is 0, only 0, then it is very important concept from the ring theory that if kernel sigma is just identity, then sigma is 1 1. It is very famous exercise. Now if kernel sigma is equal to the full ring F, this implies, because kernel sigma contains only those elements whose image is 0, it means every element of F is in kernel sigma, it means every element of F has image 0. So this implies every element of the field F has 0 image. It means sigma x is equal to 0 for all x belonging to f, and therefore sigma is a 0 max. So this was the second proof of this result. So that's all, students. These concepts of field theory are very interesting and very useful for further theory. Okay, in next lecture we will discuss some more important results from the field theory. So stay tuned for upcoming lecture, and if you like the contents of this video, our channel, please share and subscribe. Thank you.